All right, good morning, everybody. How's it going so far? I learned that in the lecture you finished section 8.3 today, which is basically trigonometric substitution. And I hope there you saw that in trigonometric substitution, once you perform the substitution step, then the entire integral will turn um, into a trigonometric function, right? Or combinations of trigonometric functions. And that's where this particular section 8.2 will become very handy in solving problems from section 8.3. So this is like a sequence wherein for section 8.3, you just add a certain substitution step, turning those radicals into trigonometric functions. And then you will end up with an integrand which involves powers of trig functions. And you go back to section 8.2 on how to integrate combinations of powers of trig functions. And I guess last time we started this discussion already. So we outlined here what to do for combinations of powers of sines and cosines. If you get one of them to be odd, right? So what you can do is take a factor from that odd power and reserve that to be your du, right? And then the remaining powers can be written in terms of the other trig functions via the Pythagorean identity sine squared plus cosine squared x. And I guess we had a couple of examples about this last time. So do you need some more examples on this case? So just let me know and I'll read your comment later. But the other case is when both of them are even. So it is impossible to isolate one factor to be your du because that will leave you with an odd power which cannot be written in terms of the trigonometric functions nicely, right? Because you will have a square roots there. So if both of them are even, then you should use this half angle identities for sines and cosines. So this is something that you have learned or you have encountered in your pre-calculus or algebra classes. So that's one thing about this particular section. You need to remember these identities from your previous classes. So even though you already graduated from algebra or pre-calculus, you still need those identities because they will keep on popping up in calculus. All right. And then later we'll go to the other case, which wherein you have combined powers of secants and tangents or cosecants and cotangents, right? So let's see some examples first about with sines and cosines. If I remember it right, we have some done last time. Actually, we had done two. Let me see. Oh, by the way, before you try using fancy techniques for powers of trig functions, it will also be nice if you can just try to apply some basic trigonometric identities for some of them because they might work nicely. For instance, let's go to problem 21. So problem 21 looks complicated because you have irrational functions of sines and secants here. But this is one problem with trigonometric functions. We can only handle integration of trig functions with the same argument. So here, on top we have x's inside the sine and secant, but in the denominator we have a 2x inside the sine function. So that makes this integral a little bit complicated. So in order to remove that complication, you need to try to use trigonometric identities to transform them in terms of the same arguments, right? So here, if you remember, I can use the double angle identity in the denominator. So sine 2x is actually just equal to 2 sine x cosine x dx. Again, in the denominator, I apply the double angle identity. And the nice thing about that, this sine will be canceled by the sign below. And so I'll have 1/2 secant x over cosine x dx. But again, here use substitution will not work. But actually, you can again try trigonometric identities first, because the 1 over cosine can be written as secant x, right? So essentially what we have here is equal to the integral of secant squared x times 1/2. Right? And the nice thing about secant squared x is it is elementary in the sense that we know the formula for the integral of secant squared x, right? So this would be 1/2 tangent x plus c. And that's our integral. Nothing fancy here, just application of trigonometric identities, right? Let me try another one. Let's try problem 30. For problem 30, we have sine of 2x times cosine of 3x dx. This is a bit tricky because I cannot write them in terms of sine 2x alone. So I guess my only recourse here is to write them basically in terms of the argument x alone. So that means I need to apply again the double angle identity for sine. So here I'll have 2 sine x cosine x. That's essentially this first factor here, right? And then the cosine of 3x can be expanded using the sum identity from trigonometry. Remember here, you can imagine cosine 3x as cosine of 2x plus x, right? So I split up the 3x into 2x plus x. The reason why I want to do that is because we have the addition formula for cosine. It says that cosine 3x can be written as cosine of 2x cosine x minus sine 2x sine x. Right? That's from the addition identity. So now I can further write the second factor here, or the second group, in terms of the argument x. So cosine 2x, I'll write it as a 2 cosine squared x minus 1. That's the identity for that. Okay, so that's what happened there. So I still have a cosine x there. And then again, sine 2x is just 2 sine x cosine x times sine x dx. All right. Or I can further simplify this as 2 sine x cosine x. And then I'll have a what? 2 cosine cubed x minus cosine x minus 2 sine squared x cosine x dx. All right. That's a mouthful of substitutions of trigonometric identities there. But yeah, we arrive at this point, and now you need to think of what would be the nice substitution here, right? Or is it possible to have a simple U substitution without appealing to complicated techniques for powers of sines and cosines? Well, you will be good if you can just isolate one trig function and express all others in terms of the other trig function. So what I'm saying is, if I reserve the sine x to be my du, right? So essentially, I'm planning to let u to be equal to cosine x. Will that be possible? So that means, can I write all other factors in this integral, or all trigonometric functions in this integral, aside from that highlighted sine x in terms of cosine, right? So this cosine is fine. This is also fine. This is fine. This is fine. Oh, my problem is sine squared x. It's still a sine, but I can use Pythagorean identity for that, right? So essentially, I can write the integral further as 2 sine x cosine x times 2 cosine cubed x minus cosine x minus 2 times 1 minus cosine squared x times cosine x dx, right? So now it means that the only sign that remained is that single sine x that I am reserving for the du, okay? So that means here I can let u be equal to cosine x, and that will require a negative sine x dx for the du. Now I have a negative there, and I have a 2 in front of the integral, so I'll have a negative 2 outside. Then integral of u times 2u cubed minus u minus 2 times 1 minus u squared times u du. And then let's just perform the multiplications here. So we'll have 2u to the fourth minus u squared minus 2u squared plus 2u to the fourth. Is that correct? So I hope you guys are checking my arithmetic here. Oops. We can further simplify here. I can have a 4u to the fourth minus 3u squared du, which is nice, right? We just have a binomial here. So the integral is negative 2 times u to the fifth. You have a 4 there, all over 5 minus 3 u cubed over 3 plus the arbitrary constant c. So essentially we'll have negative 8/5 of what was u? U is cosine x. So we'll have cosine to the fifth x minus cosine cubed x plus c. All right, is that good? Any questions with the solution? Yeah, that was long, but you see that this is just a clever play on the trigonometric identities and the u substitution. We manipulate the given integrand using trig identities until it is possible to let u be equal to one of the trig functions, and then the other, and then all other factors will be expressed in terms of the other. Oh yeah, thank you, Kevin. Yeah, that should be a -2. Oh, +2 rather. Yeah. Okay. Okay. So let's see another one. Did you have the time to look at the worksheet and try some of the problems? Now, I highly suggest that you do, because here in these exercises, you will really play with the trigonometric identities. Okay. Oh, by the way, there are some times wherein you don't need to write everything down in terms of the argument x, as long as it will become uniform in the problem. So, for instance, let's look at problem 31. Okay, for problem 31, you have cosine to the fourth. Cosine of 4x times sine 2x. Dx, right? So unlike the previous case wherein I was forced to write everything in terms of the argument x inside of the trig functions, here I can just settle to have 2x inside the arguments. Because the first step is to write cosine 4x using the double angle identity. So you can write it as 2 cosine squared of 2x minus 1. So basically, that's the double angle identity applied to cosine 4x, okay, times sine of 2x dx. The nice thing about this is I can actually proceed with the u substitution right away, because you see the cosine has 2x inside of it, and the sine also has a 2x inside of it. So I can deal with that as long as they have the same arguments. So here I can let u to be equal to cosine 2x. So du will be equal to negative 2 sine x, negative 2 sine of 2x dx, right? So that means the original integral is simply 2u squared minus 1 times negative du over 2. Right? So sine 2x dx is negative d over 2. Okay, and then hence we have negative 1/2 Then the integral would be 2u cubed over 3 minus u plus the arbitrary constant c. So I took the -1/2 out, then integrated 2u squared minus 1. And then I'll revert to the original variable, then multiply everything by -1/2. So I'll have negative u to the third, but that would be cosine cube 2x all over 3 plus 1/2 of cosine 2x plus c. Okay, I think that's it. Any questions so far? So these are some of the tricks that you can employ. Of course, you could have done a longer solution wherein you write everything in terms of the argument x, but that would be painful and even much longer, I guess, with with our solution to problem 30. So that's a lesson that you can stick to an argument other than x as long as it is uniform along all trigonometric functions. Okay. Am I going too fast or is it good? Because I'm a bit nervous now with your reaction or non-reactions. How are you feeling, guys? That's fine, Kevin. Usually, really, it takes a lot of practice to master this technique because you need to be familiar with the possibilities. Okay. And again, the crucial point here is to play with the trigonometric identities. Okay. All right, let's try problem 33. Okay. So for problem 33, you have sine to the 3/2 x cosine cube x dx. Of course, the power of sine here is neither odd nor even because it's a fraction. But luckily, we have an odd power for cosine. So we can still stick to the first bullet we had in the beginning of the worksheet and isolate one of those cosines and reserve that to be our du. So what will happen is this. I can split it up as this and reserve this for the du because that's what I do whenever I see an odd power. So I guess that's a general rule or that's a general approach. When you see an odd power, isolate a factor and that will be your du for later, or that will go into your du. And then the remaining even power could be written in terms of signs, right? That's why it's nice to begin with an odd power, take away one of the factors, and then you will be left with an even power. And that even power can be expressed in terms of the other trig function using the Pythagorean identity. And I guess that's the basic principle for powers of sines and cosines. You want one of them to be at least even. When both of them are, one of them is odd. The other case, we'll deal with it later, but let's continue with this. So I'll have it as sine to the 3/2 of x times 1 minus sine squared x cosine x dx. And now I can let u to be equal to sine x, because remember, we are reserving the cosine x dx to come with the du, right? And luckily here, it's exactly the du that we need. So here, perform the substitution. Sine x is u. So the first factor is less intimidating now because it will just be u to the 3/2, which is a simple power, right? And then we'll have a 1 minus u squared times the du. And now we have an algebraic expression here. Be careful. Use loss of exponents here. So we'll have u to the 3/2 minus u to the 7/2 du. And then integrate. We'll have u to the 5/2 all over 5/2 minus u to the 9/2 over 9/2. plus the arbitrary constant c. And then we revert to the original variable. So we have 2/5. What was u? U is sine. Sine to the 5/2 of x minus 2/9 sine to the 9/2 of x plus c. And that's our integral. And I hope it's making sense now why what to do whenever you see an odd power of either a sine or a cosine. Automatically take one of those factors, reserve it for the du, and then the remaining powers can be expressed in terms of the Pythagorean identity, right? So essentially it will be the other trig function, which will serve as your u. The reserved du will perfectly fall into its place, and then your integral will just be sum of powers of the variable u. Okay. So the difficulty, at least that I see for powers of sines and cosines, occur most when you have even powers, right? So for instance, I don't see, probably you already answered problem 16 in the lecture. So I'll add this question, which is integrating cosine squared x times sine squared x dx. Okay. Now, the problem with this integral is that we don't have an odd power, so we cannot apply the principle that we used for the previous problem. You cannot simply isolate one out of either the cosine squared or the sine squared, because that will leave you an odd power, which you cannot properly express using Pythagorean identity. All right. So whenever you have only even powers, then you need to use the half angle identity I wrote at the beginning of this the worksheet. So what I mean is that here, cosine squared can be written as 1 plus cosine of 2x all over 2. And then sine squared can be written as 1 minus sine of 2x all over 2 dx. And the nice thing about this half angle identities is that they reduce the power down from power 2 to power 1. But that comes at a cost. Sorry, it's already Friday. That's not sine, but it is still cosine. Yeah, so we were able to reduce the power down to 1 from a 2, right? But at the cost of increasing the argument. But the argument doesn't matter as long as we have the same arguments for both of them. Okay, so now after using the half angle identity, we carry out the multiplication and try to see what integral we need to deal with. So I have 1/4 in the denominator, or sorry, 4 in the denominator, so that can go out of the integral. Multiply the numerators, you'll get the 1 minus cosine squared of 2x dx, which is again an even power of cosine. But I don't want to work with 1, so you can use the half angle identity at this particular point. Replace cosine squared 2x by the half angle identity again. But I'll prefer to use Pythagorean first, so that I don't need to worry about that first term 1 there. So remember, 1 minus cosine squared is sine squared of whatever the original angle is. And then it's an even power of sine. So I'll use the half angle identity, but recall that if you have a sine squared of theta, that's equal to 1 minus cosine of twice theta all over 2. So that's the formula. And here, our theta is 2x. So if I will apply the half angle identity, so theta will be replaced by 2x. So the 2 theta there would be 4x. So essentially, this would be 1/4 integral of 1 minus cosine of twice theta. So that will be 4x all over 2 dx. Then this would be a 1/8 integral of 1 minus cosine of 4x dx. At this point, I can let u to be equal to 4x requiring du to be equal to 4 dx, or dx is equal to du over 4. So if we do the substitution, we'll have 1 minus cosine u, and then dx is du over 4. So we'll have a 1 over 32 here. Integral of 1 minus cosine u du, which is essentially u minus sine u plus the arbitrary constant c. And all that remains is to revert to the original variable. U is 4x minus sine of 4x plus the arbitrary constant c. Again, that's a long one, but again, the principle is whenever dealing with just even powers of sines or cosines, your go-to identity is the half angle identity. And it seems weird because when you're doing algebra or pre-calculus, probably you spent just a little amount of time playing with the half angle identity, but when you go to calculus, that will be extremely helpful whenever dealing with even powers of sines or cosines. Okay. Any questions, clarifications? Again, I understand it will take a little bit of time, not just time, but also practice for you to really master the techniques for integrating powers of trig functions, but they basically boil down to applying trig identities. All right. So do you want to jump now to powers of secants and tangents? Okay. So let's go back to the top and then write something here. Okay. So the second case would be for combinations of powers of secants and tangents. And here, there are two elementary or basic cases. Case number one is that if m is even. Okay, so if the exponent of secant is even, no matter what is the exponent for tangent, what you can do is to reserve a secant squared for the du. Okay, so what is the effect of doing so? Because if m is even, you will reserve a secant squared for the du. So you will still be left with an even power for secant, right? So you have even power of secant, you take away secant squared. So you will be left with another even power of secant. And for that, you will use the identity secant squared x equals 1 plus tangent squared x. And then after using this Pythagorean identity, you can let u to be equal to tangent. So, and then du will be secant squared x. And then the other case is when n is odd. When the power of tangent is odd and m is at least 2, okay, what you can do is to reserve a secant x tangent x for your du and use this identity, another Pythagorean identity, and use tangent squared x equals secant squared x minus 1. So if the power of tangent is odd and secant is at least, I guess it's at least 2, so that could be greater than or equal to 2, then reserve a secant tangent for the du, and that's a hint. Since you're reserving a secant x tangent x for the du, then that means we are targeting u to be equal to secant x. So everything that remains should be expressed in terms of secant, and for that we have the identity tangent squared x equals secant squared x minus 1. And then the unfortunate case is all other cases we don't have any specific guidelines. So no general guidelines for other cases. Probably here you can use IBP or successive integration. I'm hoping to be able to show you a quick example of this towards the end of the lesson, right? Okay. But before I do, I see Christina sent a question in the chat. Let me see. Yeah, problem 12. Yeah, you're right. You're right, Christina. For problem 12, none of these methods will work. She's referring to, let me just write that down here. She's referring to the integral of sine x squared dx. This is not elementary in form. The solution will involve the Fresnel integrals, but that is beyond the scope of the course. Actually, even undergraduate math majors might not have met Fresnel integrals. So sine x squared cannot be solved by u substitution, integration by parts, nor by trig powers. As well as the integral of e to the x squared dx. This is a seemingly unsuspicious integral because it's very simple, right? If you look at it, it's very simple, e to the x squared dx, but actually it doesn't have a closed form antiderivative. So you cannot integrate it by hand exactly. So this will involve the imaginary error function, which will still not give you the exact answer. So yeah, this is one of those integrals. These two are examples of integrals that cannot be evaluated by hand, okay, by any method, even within the course or outside the course. So yeah, and that's one difficulty with integration. We cannot integrate everything. Even after you learn all the techniques in Cal 2 or even all the techniques available to math majors, you will not still be able to integrate everything because some functions are simply not integrable. Okay. So I won't include that in the worksheet. So yeah. Okay, so let's try powers of secants and tangents. So by the way, these principles, maybe if you want, you can take a screenshot of it, and then while we discuss some examples for each case later. So this cases also apply for cosecants and cotangents. So same principles, then analogous identities can be used. So for instance, you'll have cosecant squared is equal to 1 plus cotangent squared. And then cotangent squared is equal to cosecant squared minus 1. Essentially the same thing for cosecant and cotangent. I guess that's the only consolation you get from these cases. And the tricky part here is the third asterisk, wherein you need to use IBP or successive integration. Okay, so let's try specific examples. Let me see. Let's try problem. Let's try problem 27. So for problem 27, we have a tangent to the fourth of pi x, secant to the fourth of pi x dx. Okay. So again, this is an example where in the argument of the trig functions are not simply x, they are pi x, but the good thing is that it is uniform between the two trig functions, right? So to make the solution easier, I'll just use a substitution right off the bat. I will let u to be equal to pi x. So du will be equal to pi dx. So the integral now will look a little bit simpler. It would be 1 over pi times tangent to the fourth u times secant to the fourth u du. Okay. And then we notice here that the exponent for secant is even, so it will fall under asterisk number 1, right? So you have an even power of secant, and we were told that one solution for that is to reserve a secant squared for the du, Okay, or for the substitution that we will do later, right? So this is reserved for. I should have used a different letter, but this will be reserved for the dw, for the w substitution, right? Okay, so this means I need to express this in terms of tangent. Okay, so that means I'll have a 1 over pi integral of tangent to the fourth u, and then secant squared is 1 plus tangent squared u times secant squared u du. Okay, and then here I can do the substitution. I will let u to be equal to tangent u. This will require dw as what we intended, secant squared u du. So this would be 1 over pi w to the fourth 1 plus w squared times dw, which is now a polynomial, which is easy to integrate. This is simply w to the fourth plus w to the sixth dw, and this is a 1 over pi times w to the fifth over 5 plus w to the seventh over 7 plus the arbitrary constant c. And then I'll go back to the original variable step by step. Remember, w is tangent u. But u is what? U is pi x. So basically I'll have this. But all u's will be replaced by pi x. Okay, so that's your final answer. And you see, it seems that we are not using any very different method as the u substitution. This is basically just a clever use of the trigonometric identities to allow us to use a u or a w substitution. So nothing new here. It's just an organized way of picking what identity to use. Okay. Let's try another one. Oh, don't hesitate to butt in if you have a question. But I'm hoping that you're quiet because the process seems to be clear. But of course, understanding the process is different from trying to solve the problems, really, because that's the only way you get used to answering these kinds of problem, right? So let's try problem 26. So you have cosecant cubed of x cotangent cubed x dx. Okay. For this particular problem, the power of cotangent is odd, and the exponent for cosecant is greater than or equal to 2. So we're good. We can apply the guideline suggested in the second asterisk. So here, I can isolate the cosecant cotangent. So I isolate a cosecant cotangent x dx. That would be my du for later. That's what I'm hoping, right? So if I take out the cosecant x, so what will remain here would be a cosecant squared. And after taking out the cotangent, we'll have a cotangent squared x here. And remember, we are reserving this factor for the du, right? So if that is our intended du, then we are targeting u to be equal to cosecant x, right? So that means the unhighlighted factors in this integral should be expressed purely in terms of cosecant, right? And that's why we needed cotangent to have an odd power, so that after taking one out of that odd power of cotangent, we'll be left with an even power for cotangent, which can be written in terms of cosecant using the Pythagorean identity, right? So what I'm meaning to say is that this would be cosecant squared x times cotangent squared of x is this is cosecant squared x minus 1 times cosecant x cotangent x dx. Okay. Now we can let u to be equal to cosecant x. That will require du to be negative cosecant x cotangent x dx, which we have already anticipated, right? So this will become u squared times u squared minus 1 times negative du. Okay, then this would be negative integral of u to the fourth minus u squared du, and that's negative u to the fifth over 5 plus u to the third all over 3 plus the arbitrary constant c. And then let's revert to the original variable. So this would be negative cosecant to the fifth x over 5 plus cosecant cubed x all over 3 plus the arbitrary constant c. Okay. That's easier than the previous ones we have answered. So yeah, and I guess that's basically it. There's little wiggle room for these types of problems. So I mean, you can play with the powers, but higher powers can be dealt with easily after you have the right u substitution, or after you have isolated a nice factor for the du, then u substitution will work nicely. But as we have noted earlier, not all powers, or we don't have a guideline for all other cases not covered by the first two asterisks. This is in direct contrast with the powers for sines and cosines, right? Because for the powers of sines and cosines, we have a exhaustive guideline. I mean, if there is an odd, then we know what to do. If both are even, then use half angle. But for secants and tangents, or cosecants and cotangents, that's not the case. So for instance, somebody asked me this during one of my CASA tutorials. I guess this is something that you met in the quizzes or something similar to this. So here you have tangent to the fifth of 9x dx. The exponent for tangent is odd. So I was hoping that this will fall under the second asterisk, right? But the second asterisk requires requires that there is at least 2 powers for secant, right? Because again, that asterisk requires us to reserve a secant tangent for the du, right? But unfortunately here, tangent is alone by itself. So I cannot isolate a secant tangent in preparation for the du. Okay, so that means this will fall under the third asterisk instead. We are left alone in the dark. But then what you can try to do is still play with the trig identities. I mean, the best thing we can do here is to split it up into this. Because we are limiting ourselves to using the least or the most basic trigonometric identities, right? So, and for that, I need a tangent squared, because the tangent squared can be written in terms of the secant, right? So we can write it as secant squared of 9x minus 1. And I did that because remember, we can fairly and easily integrate a tangent when it comes with a secant, right? Or powers of combinations of secants and tangents. So after that Pythagorean identity, you can look at it as a sum. So we'll have a tangent cubed 9x times secant squared 9x minus tangent cubed 9x dx. And we can split this into two integrals. So for the integral, for the first integral, you'll have tangent cube of 9x, secant squared 9x dx, right? That's the first term. So here we can let u to be equal to tangent 9x, because here we have an even power for secant. This will fall under the first asterisk. Whenever you have an even power for secant, you can isolate that for the du and express everything else in terms of the tangent. But everything is prepared here. You can simply let u to be equal to tangent 9x. So du will be equal to 9 secant squared 9x dx, which is fine. We'll just need to have a 1/9 outside. Then this will just be u cubed du. Okay, and this simplifies to 1/9 times u to the 4th all over 4 plus the arbitrary constant c. So this will be u to the 4th. That's tangent to the 4th of 9x over 36 plus the arbitrary constant c. Okay, but that's just for the first term. So we're done with this. That's evaluated. So what remains to be evaluated is the tangent cube over there. So let's do that here. But again, this is a tangent by itself. Neither asterisk 1 or asterisk 2 will apply to this. So I'll try to use the same trick as we did before. So I can write this as tangent squared 9x times tangent 9x dx. And again, we isolated the tangent squared because we can write it as a secant squared minus 1 times tangent of 9x dx. This guy will become the integral of secant squared 9x tangent 9x minus tangent of 9x dx. Then I can split this up into two integrals. So I'll have a secant squared 9x here, a tangent 9x here, dx, minus the integral of tangent 9x dx. Okay, and for the first integral, you see here that secant has an even power. So that means we can use asterisk number 1. Again, that even power for secant, from there we can isolate the secant squared, and that will be our preparation for du, right? So which is the same substitution as we did from above, right? So here we can let u to be equal to a tangent 9x again. So du will be 9 secant squared 9x dx. So what we'll have would be this integral of what? I'll have a 1/9 outside, and then we'll have u du minus integral of tangent 9x dx, right? So I am continuing this equation over here, okay? So this is 1/9 u squared over 2, and then the integral of tangent 9x, there's a formula for it. It's elementary in form. So this is minus ln of the absolute value of, I guess this is secant 9x all over 9 plus the arbitrary constant c. There's an over 9 because here I will let w be equal to 9x. Okay, and then I'll revert to the original variables. So I'll have 1/18 times u squared. So that's tangent squared 9x minus 1/9 ln of the absolute value of secant 9x plus the arbitrary constant c. But this is just for tangent cubed 9x. So therefore, finally, we get the integral for tangent to the 5th 9x dx to be equal to, let's combine the things that we have seen earlier. So tangent cubed. So we'll have this. This is the first term, remember? And then what comes after this? We evaluated this. That's a tangent to the fourth 9x over 36 minus the integral of tangent cubed. But the integral of tangent cubed is this, so we'll have 1 over 18 tangent squared 9x plus 1 over 9 ln of the absolute value of secant 9x plus the arbitrary constant c. Yeah, that's a long one. And yeah, I guess that's a good way to end the week. Hopefully you won't see something like that in the exam. But I hope you see the process. I hope that at worst you will be given tangent cube or secant cubed in the exam, but this would be the process. All right. So as I mentioned earlier, this integration of trigonometric powers will come in handy when you go to section 8.3, because if you remember from the lecture, you saw that you're turning everything in terms of trigonometric functions for section 8.3, right? And chances are you will be dealing with combinations of powers of trig functions. That's why even if it's section 8.3 already, you will still need tools from section 8.2, which is powers of trigs, in order to evaluate some of the integrals that you will encounter in section 8.3. But there are some cases from section 8.2 wherein you will need to use either U substitution, which you learned back from Calculus 1, or you'll need integration by parts, something that you have learned from section 8.1. So it is really a chain of methods that the latter methods might depend on the earlier ones. Actually, if I want to I can actually design a problem for the exam, only one problem that will require you to use all the methods we have discussed. But hopefully, and luckily, you will not be dealing with that, and you will be evaluated on separate problems. But yeah, it's possible that for one crazy integral, you might need to apply all of the techniques that you will be learning in chapter 8. Okay, and with that in mind, let's end it here. Thank you for coming. Have a good weekend, everybody. Uh, Try to answer exercises from the worksheet. Let me know on Monday if you have some questions on that, or if you have some problems from the quizzes or the homeworks. I can help you with them on Monday. But I think we will focus Monday for section 8.3. Okay, everybody. Goodbye.